it was very tough, right? So last day, yeah, everyone, I can see everyone already exhausted. You guys don't have any smile anymore. Well, last sections, okay? Last sections. So everyone has a data. Oh, and okay, Google Drive. Okay, I remember. Google Drive will be alive. So, maybe 1 year later or even 2 years later, you can access this one. So don't worry about it. You can also access the 2018 one. If you go to our website here, and here, this is for last year. This is a YouTube link, and then this is all the material one. And then here's for this year, and then we will make a link for the YouTube. All right, so then, so here is my folder. So I have one more extra one, but you should have 2 folders. One is the data brothers, and then data Zelevsk. And then this is what you practice with the Brandon from yesterday and today. So so Brandon showed how you can export, report. There are a bunch of files. I just saved some intermediate files because it would take a while to run everything. So, if you go next step, I will just save the intermediate one. But this is the file name, what I have from Skyline. And then here's the R script. So I will go to, so everyone has an R Studio and then have a MS Stat, right? If you don't have it, please raise your hand and then Tia will help you. Then I will start to open my R script. So, okay, here, this is the total, how many lines? Okay, like less than 200 lines one, but I just try to minimize the number of the codes as much as possible. I will set up my working directory here. And then I will load MS Stat. So just to summarize the Bruder's data set, this is spiking data set. There are thousands of the background protein, and there are 12 spiking proteins which know which protein should be changes. There are 8 conditions. However, the last condition kind of very weirdly behave. And we know the answers, so we can actually evaluate their performance and so on. So first, I will read our data set. So this is the name of the file from Skyline. And then I run it. So my computer is recording now, so a little bit slower than my original speed one though.
This script is part of the dumbbell.
Yes.
Yeah, sorry.
Yeah.
So
Yeah.
It's slow.
Yeah. Okay.
Oh, this one.
Yeah.
This one.
Maybe everyone just together try to access this. Or not, that's what, okay.
It's
See,
I can't play without the network.
Yeah. For DDA cases, what we practice for IPR, for example, IPRG data, in my computer, just data processing and testing part, it takes less than 5 minutes. But DIA case, like relatively similar number of the proteins, but like we have a much more number of the features. For this computer, for 1D DIA cases, it takes 1 or 1.5 hours. So that is a kind of estimate time. Yeah, you see, it's already take a while to just read the data set.
That's the process.
It
It depends on the
So this is just a reading.
number of processor of the computer.
Yeah, it also can be better.
This on much the RAM amount.
Sorry.
Is there more the processor that are critical or the memory, the RAM memory?
So actually, there is one of the hidden option cluster for data processing and testing. So if you're increasing the number of the cluster, actually it can be increasing much. However, we actually not heavily tested how it works. So potentially can be issues, but we still have some issues. Oh, maybe, okay, it's a running, but okay. People already heard MSDAT, maybe just kind of the, comment about the MSDAT itself. Here github.com and Choi, this is my GitHub, but first the repository is MSDAT. To submit the MSDAT to bioconductor, like set up the GitHub repository is one of the required. So you can see all my latest update the code here. So if you're not interested, don't worry about it. But if you want to look at it, here's the code, and then under the folder R, there's all the functions here. All the functions here. So if you want to make your own converter for your in-house software or other things, you can look at any other converter functions. So here's the all the options, and then you can see all the step by step actually what we are doing, like how we what kind of information we subtract, and then what kind of things we are taking care of it. So different converter actually have a little bit different depending on the data set, but majority of the processing should be the similar. And this is the converter function. And also if you want to modify the visualization, the plottings, here we have a plot functions here. For example, data process plot. Just draw the plot. This is like almost 1,200 lines, but most likely it's a checking, but depending on the situation and data set, we just repeat or small, a little bit updated and so on. So you can see here's all the options, and then you can just copy some part of it and then just modify for your purpose, and then make a new function for that one.
Where is that again?
This one is a data process prop.
Okay.
Yeah, so github.com and Mina Choi. Or I don't know, in the bioconductor, they might have a GitHub. No, they don't have it. So here's the ms.org, so our webpage for all information. So here, this one is pretty much all different package. So this is the main MSDAT. This is the MSDAT TMT package. Classification is kind of embedded in the MSDAT, but it's a little bit different. So it introduces a new function here. And then QC, and then we have a data set, publish the data set. And here's the link for data set. And then here's the example R script, how to analyze this one. So here shows something is SRM, something is DDA. They don't have DIA, but here's also Shiny app application here. So, and then this is the whole courses of what we attended. And then here's a contact. This is a link to our Google group. So if you have issues, something, you first can search in here. You have the same issues or not. If not, you can just post it here. So pretty much meeting, our TA should answer this one. If not answer, just please directly email me. Just keep trying to remind me. Like, yeah, I'm waiting for your answers. Yeah. That is the Google group. And anything else you're interested in? Oh, really? Do you have a Google account? Probably you need to sign it, the Google account.
I am signing it.
Oh, really? Okay. We will be back. Could you check it? Yes. Yes. So that is here. So you can just go. You can go to here. So GitHub, Vina Choi MSTED. Just MSTED and GitHub, and then you can find it. R folder, R folder, R folder, R folder, and then there are all the R files for different functions. Okay. Yeah, just click, and then you can just copy some of part based on your needs. So, yeah.
But this is what we're gonna need right now.
No, you don't need it. You don't need it. Like just in case you want to modify, customize our code for your further analysis. Yeah.
Yeah, that's great to see like what goes on behind.
Yeah,
different-
definitely.
Try to understand.
Yeah, so some of them already review the code. So kind of, well, yeah, they also find us some bug and then just report us. It has really make us easy to do this. Yeah. So now I have a raw data set, and then here is the first one is I just want to check how it looks like. So this is one row. For each feature and each run, we expect one intensity, one row. So I just put the one specific features as a sample name, and then here we have a the row column, one rows. And then I remember one of the questions is how actually different the Skyline report and MSD require format. Very similar. However, Skyline report actually report some extra column, which is very useful to check their quality or for filtering. For example, one of them is this truncated column, which they said this peak, this intensity is truncated or not. So this information is very unique for Skyline. So Skyline, report this and then we use this. But MSD require format actually not require this format. We just use this information. And then also here the Q value one also. So Skyline reported Q value. OpenSWAS report M score. Like different tool report a different score for their peak. So we cannot make this as required. However, we use this information in the converter and then make MSD required format. The reason why I'm telling you is if you have your own one, if you have your own the value or column about the quality of the peak, called peak intensity, you can also use that information to make a MSD required format. Okay. Then here, line 24, I just check annotation. So this is a Skyline file. So when you practice in the Skyline section, you already put all the annotation information, which means for each file name corresponding to what condition and the what biological replicate. So we don't need any separate annotation files, but just double check. Here we have 24 raw files, and for each we have 8 condition, and then for each condition we have only one biological replicate, which means 3 technical replicate. Okay? So far so good, right? I know this is really, tiny things, but I really like to checking things because I don't want to, bugging all the issues after I just run everything after a few hours. So, and then this is the first step. Okay, here's the Skyline report. First, what we are gonna do is I just want to make this to the MSD required format. So this is the report from Skyline, but I want to use this Q value column for filtering, and then I will use this Q value, and then this is my cutoff values. And then I also want to remove the protein with only one features. Then we can run this, and then it shows the progress.
Sorry, is it normal that the unique check before
Yes.
takes long time?
Which part?
Like this line before.
Yes. Yeah, it takes a little bit long. Yeah. Because here, number of the row is how many? Yeah, it's just quite long, so it's take a time. So here's the progress, and then this is much faster than just read the CSV file here. So now we are done, and then let's check it. So output of the converter function has this information. Then here is the extra things, extra step. Usually I need to convert and then I just go straight to the data processing. But for this specific data set, I actually look at the quite long time, and then I already know about this study. This is spiking. We know which protein should be changes and so on. So I can check the protein name first before I go to next step. Then here's what I did. The first, I checked the unique information of the protein first. And then it said there are 3,810 proteins are there. Then, what is this column is, I just count number of the character per in the unique protein ID. So, for example, let's say here is our protein name. So we expect the protein name should be around the 6. Maybe it can be 8 or something, sometimes a -1 to labeling. But it should not be like 20 characters or 25 characters and so on. So I just count the character, the number of the characters in the protein name. And then what I check, what is the number of the count, unique count, is like this. So for example, some protein name actually have this number of the character. Means actually they have a really long protein name. I guess protein A, semicolon, protein 2, and semicolon, protein 3, semicolon, and so on. That is first what I found it. And then here, these proteins are actually spiking proteins. So I just double check how actually recognize these spiking proteins, because it's important to when you calculate the actual performance, like accuracy and so on. So here, I just, from the pro.do actually include the unique protein name, and then among them, I just want to grab which include the specific, the characters. And then it shows the specific proteins actually have 5 different protein names. And then actually, for example, here, actually they just repeat twice, right? And then this one is actually combined with something else, and so on, right? So first, what I did, I think this one it seems like that specific peptide actually shared between these two. So I don't want to quantify this. But this one, actually, they just repeat it twice. So I just changed this name as just include only one. That kind of, some extra step I performed. So line 52, what I did is, this, for example, this 4 protein is what I already know, but the other combination things I'm not sure. So I just keep the protein name, which include only 6 characters in the protein name. So, and then now we have only 3,068 proteins are left.
I have a question.
Yes.
So, are you getting like each one of them, and you analyze the same set of peptides, and you keep the ID, and if they are shared, the proteins, the peptides are shared, you
Yeah.
choose them, leave them as independent.
Right. So I just want to use.
So you go one by one.
At this moment, yes. At this moment, yes. Because I know for this specific, experiment, I know very well because I said this is a spiking data set, I know very specific protein, this should be changed or not. Yeah. So, which means around 800 proteins ID actually not the unique protein ID, somehow is this combination of the some proteins. So almost 800 proteins ID can be affected when you calculate the adjusted p-value and then so on. So I just want a more conservative way and then keep the proteins which are not sharing the peptide. So this is the steps. This is the whole step, what I did. And then now Quant is ready to use the data processing step. And then also additional one step for here is, as I mentioned, here's 8 conditions, but the last condition actually work very strangely. So actually they generate so many false positive cases. So I assume this specific MS run have some issues. I only focus on 1 to 7 conditions. So here I just removed the condition 8. Okay. I'm just trying to explain the step-by-step what I did. But if you have a difficulty to read this code, please let me know. Okay.
Like the quantification condition.
Sorry.
The quant condition code.
Yeah.
How you read that one?
So quant is a data table, data frame. So I will show you how the quant look like. Okay. Here's the tables. And then from here, we have a condition columns. Here is a condition columns. So quant dollar means the column. So column code condition in the quant data. And then I want to get the unique information for that specific columns. Okay? And this one means, okay, from the quant, and then the square bracket, and then comma, it shows this one is which row, and then here shows which column. I want to subset the rows, and then what kind of row is if the quant condition include the last condition information, and then whole things I'm gonna minus, I'm gonna remove it. Then now the quant should have 1 to 7 condition, total 7 conditions are left. So these are the steps, and then rest of them is just straightforward. Rest of them is very straightforward. Actually, I didn't change anything. I just copied what we practiced the last time. The same one. Everything is the same, and this one, when I mentioned before, the skyline always recognized with 2 different missing value. One is NA, one is a 0. NA is random missing, and 0 we can impute it. So I will want to impute it the 0 value and run it. But I will not gonna run it. It will take, this part is the main part, take 1 hour. Okay, so then next step is a QC plot, and then next one is a profile plot. So I will just show you how it looks like. So I will open the profile plot. So here's the profile plot. It shows each features how they're labeling. So color is peptide ion, and then different line type is fragment. And then this is this is the next one. And then this is the next proteins, and the next proteins, and then so on. Okay, so this is the original profile plot, and the summarize with the summarization is here is what the MSF performs. So they summarized all feature per run based on the Headmaster algorithm, and then it showed the run run level summarize the plot, and then we will use these value for hypothesis testing. Okay.
That is the average.
That one is actually we covered from Monday to Wednesday heavily, but I can talk to you after like what's going on. Yes.
So the conditions are ordered alphabetically.
Yes.
So what if I have like some weird names like control, 1 hour, 2 hours?
Yeah.
Can I manipulate the order?
Absolutely. So here, okay, it's a good time. So here we make a plot, and the next one is we need to set up the metrics, right? So what we have to do is always we need to check the order of the condition. So for example, quant levels, they want to check the levels. Levels means like order of the condition. So process quant and then process oh, I didn't call it. Okay. I need to call first. Yes. So process data and conditions. Oh, so group original. So this is the order. Here, first line, this one. If you want to change this, we can use the factor. I just want to factorize again. And then, for example, here they can assign it. For example, okay, I will factor this. And then here I can set up the level differently. Here, for example, C, now I want to S2 first. And the S1 first, and then S1, and then S3, and blah, blah, blah. Okay, so this factor function can change the order of the, the levels.
So group original.
This one. So you need to click, you need to call
I
it.
did.
You did? And this one is not working?
Object group original.
Could you help me? So here we have a 7 condition, 1, 2, 3, 4, 5, 6, 7. And then here I just want to calculate for all the pairwise comparison. So I just set up the comparison. For example, here, first position is for first condition, and second one is the second condition. So it is condition 2 minus condition 1, and so on, right? So if you run everything here, and then we have a total 20, it should be 21 though, the 21 comparison, and then you can just go straight for the group comparison functions, and then just save with the different file name, and then you can just draw the order volcano plot, right? So it's a very straightforward after that, right? So always annotation file, and then this make a matrix for group comparison is a very key point for your analysis. Okay. And then I will go ahead to another data set because I want to show something else for something else. So for here, slabs, I don't know how can I pronounce this name though, but there are two folders. So as the Brandon explained, we have two different processing procedure we perform. The one is to use everything, and the next one we actually filter out all the feature which is less than 20% CV or something. So we have two different inputs. So what I did is, okay, start with the two different input and then go through everything in MS stat, same stat, and then how how we can compare. What's the difference? That is what I did. So here, I just click the old folder, and then here's also script, and then here's the data set. And under the backup, I just post all the result, intermediate one.
Can you go back again?
Okay, here capstone, and then data, select, and then all, and then here we go. So you can click the R script. Okay. Same skyline output. So we don't need to change any parameter. Just change the file name, and we need to change the metrics, but everything is just same, right? So here I just change the name, and then exactly same, and exactly same, and so on. So here's the backup. Before I just move on, I also want to say, whenever you run MSDAT, two files automatically generated. The one is a session info. Session info show what version of R or the package you use. So for example, here I used R version 3.6, and then also version for other package include MSDAT. So when you report or submit your result, you actually should say this. I used the R 3.6 and then used the MSDAT package 3.16. Also, another file is a log file, MSDAT log file. So when we already talked about the Google group, people have, I have an error message. Okay, so what should I just start it, right? So that's why I said, could you send me your, first you need to check that you have a correct version. And then, let's see the more details of where actually stop it. So here is the MSDAT log files. The first is the same as the session info. It also showed the R version and then package and so on. And then they started to do something more. So you go through the data processing functions, okay, required input, okay, what summarization method, they just report what parameter you use in the data processing. And then here is this much missing value you have. We perform the log2 transformations and then so on. And then here you use the normalization, constant normalizations. And then here is the one of the, maybe you are interested in, this is the cutoff to define the censored missing. So this is, by each experiment, MSDAT decide based on this data set. And then here's a summary. And after done, it shows that you go to the group comparison function and so on. If something happens, they're gonna stop somewhere. Then it actually helps us to where actually start the error. So it is easy for us to where actually we have to look at it. And for example, group comparison function, here's also they report some errors. So here's they said errors means result, they are NA. Some column is NA because there are measurements only in some groups. So basically they want to compare two groups, but specific one group have a completely missing. So that's why we cannot report it, and then we report this is NA value. But they actually report anything happened just here. So you can see actually what happened during your analysis. Okay. So for us, from here to here is quite important. This is a kind of the most important part because it can be really, there are many options possible during these steps. Okay. So that is log files. So here's all the result one, and then let's go back to the data data set left sec. And then there's another folder, log CV, which is a new skyline output based on after the filter out some features, right? So same format, but different name. Script is everything is same except the first input file name. So everything is exactly the same. I didn't change anything at all. And then I just saved the output is here. Output under the backup. Because it will also take 1 hour over there. So what I'm gonna do here, I just come back and then I want to compare these two results. I just want to compare these two results. So I just open this one. So this is not related MSDAT. This is just a general, R stuff. So I just run the first two packages to summarize or manipulate the data set. Then, okay, before that, I will remove our environment completely. I just make everything is clean. Here's empty. And then I will call our two results. One is from all, and then I have this name. Then one is from row CV, and then this name. Okay. I should set up the working directory here. Everyone wrote the data set. Okay. First, you can see there are different number of the rows we have, right? This is the first investigation. And then let's see what's going on over there. So how it look like? The first one is just table from MSDAT Google group comparison. So they have a protein ID, and then for each protein, for which comparison, what is the estimate log for changes and standard error, and also p-value, and so on, right? And then the second one, another table, also have a exactly same format. Line 11, I just make another column. I just want to another column because I want to merge these two tables, but before merge, I want to annotate these rows came from which data set, and then the other one came from which data set. So first data set I call the data came from all, and then the other one is data came from the row CV. Then if I run line 13, now I have an extra column called data. Then line 16 is just merge these two data sets. Okay? So here you can see the number is just sum of these two ones. Then what I'm gonna do is there are two different group comparison results, and then I will extract the protein list which is significant. Then I just want to compare some protein probably significant for one specific cases, or some proteins only detected as a significant for the other cases, or sometimes they just in both cases they detected as a significant one. But most likely we want to check some protein detected as a significant for one specific cases, and what's the reason? What's the reason for these two different results? So line 22 from test. The test data table merge everything. So p-value is not NA, which means there are no some issues, and then less than 0.05, which is a significant proteins. Significant proteins and for specific comparison. Then next step is I just want to count it how many proteins are significant for each comparisons. So here we go. So this is the data with all features, and this is the after we filter out in the skyline, and then this is the number of the the proteins for this specific comparison. Okay, so if I just repeat what the experiment is they have 6 different time courses east. So we expect they actually give some stress, and then based on different time courses, we expect something is to happen, and then we expect the more number of the proteins will be detected as a significant. So here, first, like after a few minutes, not many, but after, like I think this is 2 hours. After 2 hours, we can see like around the 700 proteins are significant, and then we expect it should be keep increasing, like something increasing and decreasing, increasing. That decreasing, we expect this to keep increasing. But if I used all proteins, you can see they are increasing, however, certainly decreasing, and then just going up again. So I will look at what actually happened this T3, which actually have a more difference between 2 cases. So first, to compare these 2 cases, I will just introduce how to use the make-up Venn diagram, like just a basic one. There are multiple packages to draw the Venn diagram, like there are so many packages. So one day you use this Venn diagram, but after a few months, you probably can find another better package, and after a few months, you also can find another better package. But I will start the one very simple one, basic one, and then I will show some other, like a little bit different one. So first, what I did is, from the significant protein list, I subtract the protein which actually came from the all. So here, now we have 519, so which is actually the same number as here. And then row CV ID is protein ID, which is a significant the differential abundance between the T3 and T0 from the row CV data set. And then now we have a 373 proteins are there. Then I will use this G plus the package. If you don't have, you can just now you can install this package one. So all ID, how it look like? All ID is protein name, and here row CV is protein name, and then 2 vectors we have, and then they check which one is overlapping, and then count number, and then make a Venn diagram. Okay, so here is it. Yeah, it's kind of a little bit weird, right? So not that like the pretty. So here is another package of what I found. If you don't have it, you can find here. First, when I try to need this new package, also very tiny mistake, I keep have an error message, and then this is not what I expected. The reason was the previously the lowercase v, and here's a capital V function name. Then exactly same, and then this is what they show. So when they make a Venn diagram, they actually adjust a bit, based on the size, and they make like something like this. But sometimes it's not working if you have more than 3 groups. Sometimes it's not working, but this is kind of. And then there are some options you can change the color or anything over there. Okay.
Can you extract from the Venn diagram the IDs to see what's common, what you need in the 2 series?
Here we cannot find it here. Yeah, they actually not report exactly what is unique or something. But that one is actually, yeah, we can very easily find this. So for example, if you want to find the list of the protein, like intersect between 2, you can do is intersect all ID and row CV here. It will show the 275 one. If you want to find something, some protein is only here, or here, like separately, I can do so set difference, show the difference between all ID, row CV ID. So basically this one show probably 244 protein list, which means from all ID and then remove any overlapping one. Yeah, so you can find the list over here. Yeah. So what I'm gonna do, I will look at some of the proteins here or here, and then I will go back to our original profile plot, and then actually see what's the difference. What's the difference between the two original quantified intensities? So I will subtract the T3 minus T0, and then here I just want to find some checklist. Means for each protein, I just labeling. For example, first protein, that is significant for two cases, two data set. And then, for example, this one is significant on the all, but not significant for the row CV cases, right? So I just can subtract the protein ID there. And then here is the some cases, line 63, YBL020W1. So here is the result. So estimate log to 4 changes, they have the same directions, but the SE is different, but the other one is NA, and then something is actually they show some p-value. So what I did is I go back to the I want to go back to the plot and then want to see actually how the quantified intensity for this specific protein look like. So I open the protein summary plot. This is from all, for all. And then other thing is I want to go to the low CV1 and go here and then open another one. And then I will find that specific proteins. YBL here. Okay. Yes?
Why are the profiles different?
So, if we just, let's go back to the what we practiced with the Brandon just before this session. So for that specific data set, he processed two different ways. One is just go through whatever he did. And then the other one is he already have some other 8 different MS1 information. And from there, he just found some features which actually like more noisy, like higher, some CV, like higher CV features. And then he removed that specific feature for, data set, and then just calculate and quantify it. So like total number actually will start, so it can be affected several different ways, quantify itself, or calibration, or like the Q value calculation FTR. So that's why actually the output quantified value is. So this case, if you remember here, the all, that is all, actually have a no. They have an estimate for changes, but no other just p-value, and next one is here. So here, this versus this, they actually look significantly different. But here, this case, we can estimate the difference. However, we can calculate the p-value. There's only one value for in these cases, right? And then I also look at some other cases. YBR 006 here. Here. This is also same proteins. Same proteins. Actually, this one have a more features here, more noisy cases, and then it actually affects each quantification cases. This one looks much cleaner and then more consistent. And then here and there, actually, with the quantified and the summarized value looks quite different, and then generate a different conclusions.
So basically, those are all those lower ones are peptides that you got rid of because their
Yes,
error was so high.
exactly.
So now you're just summarizing
Right.
the best peptides.
Right. And then if you see here, this is quantified, and then here is not quantified or something like that because of like another kind of the calculation. Yeah. And that is when we only.
Excuse me, so the final conclusion for that specific protein is that when you get this CV correction, it's more accurate from a
Absolutely.
quantitative
Yeah. So
perspective.
right, because for that we need a prior study, right? 3-year study, like another pilot study, we can know which peptide have more and which don't. But this is quite rarely happen, right? This is not easy to that kind of situation. I think that is a kind of the major. Right? And then I just want to one more thing. So this is a case that is detected as significant in the all cases, but not in the raw CV cases. Something like this. So for me, this is also, I don't know why, but this is more like the stable, and then I can see here's more like decrease in pattern or something like this. I think that is also really depending on the total number of feature, how actually we are doing the normalization and so on. So yes.
Sorry, this PDF are automatically generated from the code?
From yes, MSTAT. So this is the profile plot after the data processing. So you can just make everything just here. Yeah. So what I want to deliver from this case actually is really matter for how actually you use the data processing tools. Second one is this is right very unified RSP. You can just change the CSV file and click, and then everything will be generated, right? And then you will look at the only just okay, this is the table for testing result, and then I will look at it only. But I want to look at the your the testing result, and then I hope that you can just go back to the all the visualization what we show, and then try to look at the actually is this working well or something, and other thing you unexpected or something like this. So just want to show the overall. I cannot tell here which one is the better or right answers, but just want to show the whole process. So yes, so this is how I just compare these two cases. This is for the DIA by the Skyline. However, if you are already attending our MSTES section, probably you already see some files. So here's the Google Drive, and under the program 6 StatMS, here etc folder, there are two different DIA cases by OpenSWAS and then Spectronaut. So there are small example over there. So other step is also exactly same. Only difference is the converter function part. So Spectronaut, we use different converter function. On OpenSWAS, also different function. For DIA cases, we have extra options in the converter functions. So I just want to make sure you have to keep in mind that option, which option you have to use for that specific converter. Okay. So this is all I prepared, but I'm very happy to answer your all question related to the MSTEP. Yeah, related to the MSTEP part. Anything you are interested in the MSTEP part or MSTEP TMT, Ting is here, so we can also answer this. Yes. Yes.
Mina, could you remind us of like how it does like calibration, like how it looks at the whether or not it's quantifiable and like models like your value?
That one?
Yeah, just like an overview.
That one is not actually our part, like more Skyline, they are doing that part. So, yeah. Sorry. Yeah.
Along these lines, there isn't a LOD module in MSTEP.
That is actually a little bit different though. It's a little bit different. We have a completely different input format for that part. So because LOD, LOQ part is not generally a biological study one, we actually need some dilution series of the data set, right? And then actually they require a different format one. So a little bit different, but that is also available in the MSTEP module. So one part of the MSTEP module. So if you install the MSTEP, you can actually get it. So MSTEP.org. So here it'll be LOD part, and then here's the user manual part. So if you wrote the MSTEP part, here is the one of the input format, but this kind of information we need extra, especially concentration for LOB, LOD, right? So this is quite a little bit different.
Yeah. So then following from that, the MS stats is just going to tell us that there's a difference. It's not going to say maybe that difference is exaggerated because we're out
No,
of the
yeah, no.
range of detection.
No, no. Yeah, it's a kind of separate procedure.
Yeah.
Yeah. Yes.
Do you have any kind of script which can tell me the up-regulated and down-regulated in both cases?
So that cases, some R code can help you. So for example, here, this one is a test is to include all the test result, and then they just filtered. Or just p-value is less than 0.5, right? Okay, let's say this is the hour something. Then what we can do, if you want to up-regulate one, we have this estimate log changes, but this is a log scale. So up-regulated means plus, minus. So it should be if you evaluate. Yeah, then they actually extract rows. If this is minus, they just regulate it. Or if you want both, or this is the or. Like this. Yeah. Did you have a question? Yes.
Yeah, I think there might be more complicated. Just, is it possible to get a quick overview of how to use MSTEP to work at the peptide level?
Peptide level. Okay. MSTEP always. What actually? Okay. Let's go back to the here, and then I will just open any one of this. So quanti is the process data set, right? So this is a required format. So all the analysis, all the plot is based on the protein name. So based on the unique information of the protein name. So we just recognize, for example, first the unique protein name and the subset, get the subset, and then do anything at all. So what you can do is if you're on the peptide level, you can just make protein name as the peptide sequence. Just make this one just go to this way.
Okay, so I change the data
Right.
for running the function.
Yeah. So for example, quant protein name. We can just change the protein name column. So for example, paste quant protein name and quant peptide sequence separate by this means I want to make a peptide. The protein name column is a combination of the protein name and the peptide sequence. Or you can just simply just protein name column should be just peptide sequence. Yeah.
Definitely better to do
Right.
this way
Yeah.
to
Right.
keep the
Right. So after you finish the converter functions, just use this line and then everything is the same. Okay. This is more likely our case, but okay. So I don't know. This is make sense or not. C is actually C1, C2, C3, and C4, and then let's say A. Okay. Right. It shows A level C1, 2, 3, 4. Right. I want to change the order, change the level of the order. How I can do this? A factor A. However, I want to change the levels, order of the levels, like C4, C2, C3, and C1. Okay. Then again, now they actually change the levels. You can change the name itself too. So for example, here A, but I want to change labels. So labels. So for example, here I want to say this is S1, S2, S3, and S4. Okay. Then if I see A, now it's completely same. Yes. Level and lab. This is level is more like order of the unique information, and this is label is labels. How to label is I want to change it. Okay, very tough day. I'm done. I'm done. Okay, but absolutely happy to answer. We almost have 1 hour left, so before I just wrap up this one, please could you fill the feedback form now? Oh, maybe it's a good time to maybe introduce something new one. Thank you for reminding this. The new, we actually have a new feature in MS Stat in data processing functions. That is really new. We never post this one, but this is available in the this version. This part. So feature subject. So previously we, for what we are working for Slavsky one, we actually have a feature list from another pilot study. We know that is like lower, like the high, like low quality of the features. But without this, we actually developed some algorithm to find a feature have non-informative or have a lot of the outlier or something. So here our default is we just want to use all features. However, if you make this option is, for example, subject is high quality. I just want to use the only feature with the high quality, and then I want to remove that uninformative and outlier true, because so far our default option is false. Actually, they select the feature which is more informative features, and then remove the outliers, and then use only that intensity for next step. Yeah, so that is also kind of the new feature in MSTEP. It takes a double timing. For example, the DIA case 1.5 hour. Use this option, kind of 2 hours and 3 hours.
How does it decide that feature is
that is we are preparing the manuscript one. Also, yeah, kind of the long story one. Yeah, we also actually try to find some time, but this time, not that ready.
Can you give the key message?
So he is not here, but yes, I one of the author, but like the main developer is not here, so maybe it will be good to talk with him. He will come soon, I guess. Yeah.
Okay.
Yeah. And then also another things I want to mention was last year we had this year Wednesday we have a massive section, but last year we don't have massive section. Instead, we are more focused on the biomarker study part, like more machine learning classification, and then find the biomarker and then so on. So this year we missed that part. However, you can find the YouTube one and the material one. So if you go to 2018, the hands out, you can see here, and then that is a program 5. Then this one, the prediction one. So there's more a case study. What is the after the MSTAT? So MSTAT is just show the significantly detected as a significant proteins, but this is more likely how we can apply the protein quantification by MSTAT for the biomarker study. So you can also see the YouTube for this part. So maybe it will be good for you to, when you think about the experiment design. Yeah. Anything else? No, so brain is not that working well then. Mine too. It's not working very well. Yeah. Okay, so we have one last Rudy's talk. So don't leave, just stay here. And then we have a certificate for you. So please pick up your certificate over here.